Alright. Now, what is the next thing to do? Lambda n equal to lambda p not equal to 0, right. That turns out to be actually somewhat involved. So, I want you to all be awake, and this is I think the first time you are actually looking at circuits with more than 2 transistors, where both transistors are doing some work. In fact, we are looking at 4 transistors now. The incremental equivalent is all I am going to draw, we are going to go from there. All right. So, that is ground. So, as usual I am going to, this is VD, this is minus VD, and so this is GM N R N. Okay. So, the NMOS transistors, I am not going to mark it there, so that because it becomes very cluttery. So, this is GM N R O N is the output resistance of the NMOS transistor. The PMOS transistor is GMP and RO. Correct? Now, what are we trying to find? We are trying to find VO or the gain equivalent. So, as usual, what will we do? How will you find the gain? What did we do in the previous case? You find the Norton current and then find the Norton resistance, and then do the same thing. So, the Norton current is pretty straightforward. So, what will we do? We will put a 0 here, okay, and technically speaking, the output resistances of the transistors M1, M2, M3 and M4 are not output resistance are not infinite. So, technically it is this, there is no this node here is not 0 potential, right. However, what comment can you make about the incremental voltage at this node? So, basically, right, I mean, we know that this is going to be not 0, but it is going to be only close to 0. So, basically, if you assume that, then you can see that this voltage is going to be some minus GMN, approximately minus GMN by GMP times VD, right, which is of the same order as, what comment can you make about that quantity, folks? Roughly same order of magnitudes, that is also going to be roughly about VD, okay. And if GMRON and GMROP are large numbers, if the drain changes by a small amount, what comment can you make about the effect of it on the source potential? It is going to be divided by some large number. So, basically, for all practical purposes, because this voltage is small, all right, what is this voltage? 0, because we have put the 0 voltage there to find the Norton equivalent. So, this is small, this is 0, this is small, correct. So, for all practical purposes, even though technically the circuit is not symmetric, right, we assume that it is symmetric, and then we go through the analysis. And what comment can you make about the Norton current Ix? What is it? This will be 0. So, this current will be approximately, this will be GM N times VD, right. But there is actually a will that, what will be the voltage here? Minus GMN times VD by GMP, but technically there is R naught of this transistor, there is also R naught of that transistor, but those the GM R naught is a large number, and therefore we can neglect it. So, what is the, so effectively for all practical purposes, therefore this current is nothing but GMN times VD, just like in the case with infinite RO. Okay, let me reiterate again, right. Technically speaking, the circuit is no longer symmetric. So, you cannot assume that this voltage is 0. In fact, it is not 0. However, because this is 0 and this resistance is small, or basically this incremental, this the resistance is of the order of the GM of the NMOS transistor, right. We see that the voltage swing here is going to be small, just like VD. Okay. So, if the drains of both these of both M1 and M2 are pretty much not swinging, M2 of course is absolutely not swinging, M1 is swinging very little for all practical purposes. Therefore, remember that the effect of a drain voltage swing gets divided down by the GMRO of a device when it comes to the source. So, since the drain is swinging very little to begin with, its influence on the source potential is negligible, and therefore, for all practical purposes this voltage will be 0, right. So, what is the current in M2, drain current in M2? Sorry, this current is in the opposite direction. This current is, oh sorry, that is correct. So, GMN VD, this is in the opposite direction, this is GMN times VD. So, what is the, so Ix as before is 2 GMN times VD, all right. Okay, now is the hard part, which is, well, what is the output resistance? To find the output resistance, what do we do? We removed all the both the independent sources. So, this is ground, this is ground. Okay, so what should we do here? We inject, we apply Vx, I do not want to write test, I will just try to call it Vx, and measure this Ix. Okay. All right. Okay. Now, to do this, let us mark down. So, what is the impedance looking in here? Approximately 1 by 1 over GMP. Correct. Okay. So, what is it exactly? 1 over GMP parallel ROP, but that ROP GMP ROP is a large number. So, we neglect ROP. So, this is that looking in impedance approximately 1 over GMP. Okay. So, what comment can you make about the looking in impedance here? Remember, again let me draw your attention to this, which we have done before. Let us say you have RD here and the transistor has got some output resistance is some GM RO. What is Rin? Huh? RD plus R naught over 1 plus GMR. This we did in class, right? Not what you are saying, right? Okay. So, if sanity check, if RO is infinity, what should be the input resistance? 1 by GM. All right. Does that turn out to be right here? If RO tends to infinity, it is, you can neglect RD and therefore, the input resistance becomes 1 over GM. All right. In our case, now what is RD here? 1 over GMP plus RON divided by 1 plus GMN RON. Okay, so what can we approximate this as? Which is larger? In the numerator, which term can we neglect? Numerator. You can neglect this guy. In the denominator, you can neglect 1. So, what do we have? 1 by GMN. Okay. So, even though there is a resistance in the drain, because that resistance is small compared to, because it is small compared to the R output resistance of M1, right, you basically have, it has no influence on. This is equivalent to saying this is exactly the same argument. I do not know if you are able to perceive this, but this is exactly the same argument we made for when we did the Norton equivalent. We said even though there is the circuit is actually asymmetric, right, for all practical purposes we can assume that common source resistance, the common source point has 0 potential, because I mean the looking in impedance on the left side is approximately 1 over GMN, which is what we would have got if lambda n was 0, correct. And the what is the resistance looking in into the source of M2? 1 by GM, right. There is of course there is another RON in parallel, but again that is small. So, is that clear? Okay. So, this is 1 over GMN, all right. So, now I mean why are we doing all this? Because we are applying a voltage Vx here. The Ix has got two parts, one is like that, one is Ix is the sum of 2 currents. We want to find both the currents so that we can find Ix. So, to find this current here, let us call that Ix1, that is Ix2. How will we find Ix1? We have to find the resistance looking down from the drain of M2. So, for as far as M2 is concerned, therefore, basically to calculate Ix1, this is M2. What is there at the source of M2? 1 over GMN. And so, what is we are applying Vx here. So, what is the current? What is the output resistance looking in from the drain of M2? Pardon, 1 over GMN plus R0 plus GMN times RON times 1 over GM. Very good. So, this is approximately. So, this can be neglected, this goes away, and this is approximately 2R0. Does it make sense? Okay. So, Ix1 is therefore nothing but Vx over 2R0. So, where will that current Ix1 flow? It will flow through the drain of M2. Where must it flow out through? Where must it flow out of? It must go through the source of M2. So, this is Ix1, and then what happens to that current? It flows through the source of M1. Where must it get out? It must get out to the drain of M1. So, this is Ix1. So, if Ix1 goes into M3, M4 also, they must be, see M4 is a little bit tricky, you have to be careful, because M4 has got, you can think of it as an ideal MOSFET without output resistance and ROP. in parallel, correct. The GM part of M4 will give you that Ix1, right. All right, and so the total Ix will therefore be equal to 2 Ix1 plus Vx by Ro. Is that clear? It's actually quite subtle, and I mean anyway, I will come to the final result and then we will discuss it. So, what is Ix1? 2 times Vx1 Vx by 2 R naught n plus Vx by Ro. Where did you lose me? Oh, see, this is going through the mirror, na? This Ix1 is coming through like this and going through, creating a voltage drop at the gate of M3, but M3 and M4 form a mirror. So, that is going to cause that GM times VGS of M4 is going to pull a current. You are pushing a current into M3. So, the mirror will basically pull a current in the same direction. Is that clear? Okay. So, at the end of the day, therefore, after all this work, Ix is therefore nothing but Vx by Ron plus Vx over Rop. So, what is the resistance? Look here, what is the Norton resistance? Ron parallel Rop. Okay. Right. A lot of people would basically say, why do you have to go through all this, this analysis for this? Oh, well, why wouldn't it be okay if we just assume that this was ground? Then you will get anyway Ron parallel Rop. So, do you need all this? But you see that you happen to get the right answer, but the analysis is actually wrong. Okay. So, basically that would predict that this Ix1 would be 0. Right, that would predict that the current flowing, incremental current flowing through M3 is 0. That is not correct actually, right. Okay, though you get the same final answer. So, this is a great interview question because right, somebody asks you to analyze this and basically you will say, well, this source is grounded, and then you have Ron, Rop. Obviously, the answer is Ron parallel Rop. And then the interviewer will ask you, how did you ground the source of the common source node? And then you will scratch your head and say by symmetry, and then they will say, well, output resistance is not zero, where did you get symmetry? And then you scratch your head and then say, I do not know, right? All right, you understand. So, but this is a great way of remembering the final formula, which is Ron parallel Rop. Okay. So, at the end of after a lot of algebra, basically we see that finally the answer is Ron parallel Rop. So, what is the output voltage? 2 GMN times Ron parallel Rop times Vd. So, the gain, the incremental gain therefore is nothing but 2 GM n times Vd times Ron parallel. Does it make sense? Okay. So, that basically covers the differential pair with active load, right. Now that that finishes the discussion on the small signal properties of the differential pair.